All right, our blood vessel is 360 millimeters long with circular cross sections of varying diameter. The table above gives the measurements of the diameter of the blood vessel at selected points along the length of the blood vessel, where x represents the distance from one end of the blood vessel, and b of x is a twice differentiable function that represents the diameter at that point. Write an integral expression in terms of b of x that represents the average radius in millimeters of the blood vessel between 0 and 360. So average radius would be key. They keep giving us diameter up here and diameter here, and then they of course ask for average radius from 0 to 360 in terms of b of t. So that's an integral expression. But now, what is our average radius? This is going to tell us, this is going to total up all of our radiuses. So if I want to average, or this is actually going to total up all of our diameters. So if I want to average up my diameters, I would just do our mean value theorem of 1 over 360, 0 to 360 of b of t. And then if I throw in just an extra 1/2, that's going to divide my average diameter in half to find my average radius. And it just says write an integral expression. It doesn't say evaluate. And taking a look at B, approximate the value of your answer from part A, meaning 0 to 360 of b of t, and 1 over 720, or 1/2 times 360, which would be the average radius. So if we want to approximate it using our table, using a midpoint Riemann sum with 3 subintervals. Now if you were to graph this, 0 to 360 divided by 3 goes by 120. So here is one subinterval with a midpoint of 60. Then from 120 to 240 would be another one with a midpoint of 180, and then 240 to 360 with a midpoint of 300. So 1 over 720 times our midpoints, 30, our midpoint heights, 30 plus 30 plus 24. So those numbers came from our table, the midpoint heights. And if you graph this, which I would strongly recommend, you should see what that looks like. Go ahead and calculate that. 14, I think we're in millimeters, would be our average radius. Using correct units, explain the meaning of pi times the integral from 125 to 275 of b of x over 2 squared dx. I love these questions because there's no, it's a calculus thinking question. First off, I hope we recognize that b of x was our diameter, so b of x over 2 is our radius. And it's, so if I look inside and I call this radius squared, that is the area of a circle. So then if I look at adding up a bunch of radiuses squared, which is what calculus does, that should give me a volume. So pi r squared plus pi r squared plus pi r squared is going to give me the volume of blood in the vessel from 125 millimeters from x to 275 millimeters away. I really like the thinking on part D. Explain why there must be at least one value x for 0 to 360 such that b double prime of x equals 0. And I think there's a couple ways to go about this, but I think a really neat way to do it is to say that use our mean value theorem and start with the derivative. So b prime somewhere has to equal 0. And what I'm going to say is, because b of 60 and b of 180 somewhere in between 60 and 180, b prime of x had to equal 0. And if you draw your graph, you know, if it went up and then down, for them to be equal here and here, somewhere in between. And the key is that it's twice differentiable. Somewhere in between it had to be 0. Even if it went down, it had to be 0. It could have been 0 the whole time, but somewhere in between there, for those to be equal, the derivative had to be 0. The cool thing is, if you keep looking at your table and go, doesn't that also work from 240 to 260? And of course it does. So b prime of a second x also has to equal 0 because b of 240 equals b of 360. So b prime of some x2 has to equal 0 somewhere in between those two. So now I hope you see what we've done. We've said because b prime of x equals 0 2 times, meaning b prime of x1 equals a different b prime of x2 by its mean value theorem, b double prime somewhere in between x1 and x2 has to equal 0. That is some awesome justification. Go calculus.